In the quiet of Earth's upper atmosphere, where the air grows thin and the sky turns black, a ballet of machines endlessly unfolds. Thousands of human-made satellites, some no larger than a suitcase, others the size of buses, glide in their silent paths around our planet. They are our mechanical eyes and hands in the void, tracing weather systems, measuring magnetic fields, and peering deep into the cosmos. Each one, a symbol of human ambition, whispers a single truth: we were never meant to stop at the edge of the sky. But for every triumph drifting among the stars, there's a hidden story of failure, flame, and fragile invention. Behind every satellite that sings to Earth, there lies the brute force of a launcher, towering rockets that must perform with perfect precision. One error, one faulty valve, one reverse sensor, and decades of effort can vanish in seconds of fire. The quest to reach orbit has always walked a razor's edge between brilliance and catastrophe. The modern era of space exploration is no longer the domain of superpowers alone. The age when state-owned giants ruled the heavens has faded. Now, small teams of engineers, private companies, and restless visionaries have taken the mantle. In workshops in California, New Zealand, and Siberia, new rockets roar to life, sleek, reusable, and far cheaper than the colossi that came before them. SpaceX, Rocket Lab, Arianespace, and others compete not for prestige but for precision. The space race, once driven by ideology, has become a contest of economics and innovation. Yet, despite this evolution, the heart of the story remains unchanged. From the Soviet Soyuz to NASA's Space Shuttle, from the European Ariane 5 to the American Delta IV Heavy, every mission begins the same way, with a single moment of ignition. Fire consumes the launch pad, steel trembles, and the rocket rises. It's the moment when gravity itself seems to hesitate, when human ingenuity defies its oldest master, the pull of the Earth. This is the story of our ascent, of the machines we've built to breach the sky, and the fragile human bodies that dared to follow. It's a chronicle that stretches from the dawn of the space age to the silent corridors of the International Space Station, from the mirrored eye of the Hubble telescope to the new frontier of the James Webb, and from early flight suits stitched in rubber to the complex life support systems of the 21st century. Each of these creations, whether forged in Soviet steel or Silicon Valley carbon fiber, tells the same tale of persistence, the will to explore. But that will comes at a cost. Every new leap forward demands precision measured to the millimeter, courage measured in lives, and faith that the next launch will not end in flame. Tonight, we'll travel through that entire odyssey, through decades of technological evolution, political rivalry, and the unyielding human desire to understand what lies beyond the blue horizon. We'll uncover the silent battles fought in the vacuum of space, the hidden failures buried beneath the success stories, and the fragile thread that connects Earth to its orbiting children. Because above us, in the thin silence beyond the clouds, the machines we've made are still watching, and they're teaching us, bit by bit, how to leave home. It began quietly, almost without ceremony. In October 1957, a polished metal sphere the size of a beach ball rose from a remote launch site on the Kazakh steppe. Its name was Sputnik 1. For the first time in history, a man-made object circled the Earth. Every 96 minutes, it crossed the sky, transmitting a rhythmic, metallic heartbeat that echoed through the world's radios. Beep, beep, beep. To the naked eye, it was a faint, drifting point of light, but its implications were seismic. Humanity had breached the atmosphere. The planet itself was no longer the limit. Within weeks, governments, scientists, and ordinary citizens began to look upward differently. The space age had begun, not as a moment of triumph alone, but as a declaration of rivalry, fear, and hope. In the Soviet Union, engineers celebrated a technical miracle years ahead of its time. In the United States, that same signal was heard as a warning. Schools began teaching space science. The Pentagon founded new agencies dedicated to rocket research. Within a year, NASA was born, an organization designed to ensure that America would not be left behind. But those first machines were crude and fragile by today's standards. Their orbit was uncertain, their lifespan brief. Sputnik burned up after just 3 months, but its ashes marked the beginning of a revolution that would redefine civilization. The race for the heavens was no longer theoretical. It was political, immediate, and unstoppable. Soon came Explorer 1, America's answer to Sputnik, which discovered the Van Allen radiation belts. Then Vostok 1, carrying Yuri Gagarin, the first human to circle the Earth in 1961. In those early years, the rockets themselves were as much a part of the story as the satellites they carried. Born from weapons programs, they were the children of the Cold War, instruments of destruction repurposed to chase discovery. At the heart of the Soviet program stood the R-7 rocket, originally designed to deliver nuclear warheads across continents. Its chief designer, Sergei Korolev, envisioned something more profound. By adapting the missile's clustered design of a central core and 4 boosters, he created the Vostok launcher, capable of sending both satellites and humans into low Earth orbit. It was an act of engineering audacity. The same machine that could destroy cities would now lift humanity toward the stars. As the 1960s unfolded, Earth's orbit grew crowded. Meteorological satellites began tracking the weather from above. Military reconnaissance craft watched the enemy's movements from the stratosphere. Scientific payloads probed the Earth's magnetic field, while others looked outward, peering into the solar system. Each orbiting machine carried a fragment of human curiosity. Each launch a risk balanced on columns of flame. The concept of space infrastructure didn't yet exist. Rockets were disposable, their remains falling into oceans or deserts. Every launch was a singular gamble, an enormous investment that might vanish in the silence of failure. Yet every success proved the impossible possible, and the cost was accepted as the price of progress. By the early 1970s, satellites were no longer just symbols of power, they had become vital instruments of civilization. Communication satellites linked continents, weather satellites saved lives, and navigation systems began to map the planet with precision never before imagined. The invisible web of orbital machines had become the nervous system of modern humanity. But all of this progress rested on a single fragile principle: the ability to reach orbit safely, repeatedly, and affordably. That was the next great challenge, one that would shape the next half-century of exploration. From the frozen plains of Baikonur to the coastal jungles of French Guiana, engineers began to dream of new launchers, stronger, cheaper, reusable. Rockets that would no longer die with each mission, but return home to fly again. The dream was bold, the path uncertain. The era of the expendable rocket was nearing its twilight, and a new vision was about to rise on pillars of fire. Every journey beyond Earth begins with an explosion, not of destruction but of release. Millions of kilograms of propellant ignited in perfect synchronization, harnessed by mathematics, structure, and nerve. The rocket, our most violent invention, became the only bridge between humanity and the heavens. In the early decades of the space age, this bridge was fragile and costly. Launchers were built like monuments. Massive, single-use towers of fuel and steel that rose once and then perished in the atmosphere. Yet within their brief, blazing lifespans, they carried the weight of nations. Among the giants, none was more enduring than the Soviet Soyuz. Its design, simple yet elegant, was born from Korolev's original Vostok lineage. At its heart, a central core surrounded by 4 tapered boosters, each known affectionately as carrots in Russian. When fully assembled, the Soyuz stood more than 50 meters tall, weighing over 300 tons when loaded with fuel. It was a marvel of reliability, so robust that even 6 decades later, its descendants still carry astronauts to orbit. The Soyuz's genius lay in its simplicity. No exotic alloys, no overcomplicated electronics. Just proven physics, modular engines, and a design that could be repaired or replicated endlessly. Where the American space shuttle would one day consume billions per mission, the Russians could launch 20 Soyuz rockets for the same cost. It was the quiet workhorse of space exploration, ferrying crews to the International Space Station long after the shuttle's retirement. Across the Atlantic, the United States took a different path. The 1970s brought the dream of reusability. The Space Shuttle, a machine both rocket and aircraft, designed to take off vertically, orbit the Earth, and glide home like a bird. It was a feat of extraordinary engineering and extraordinary risk. The shuttle promised cheaper, more frequent access to orbit, but in reality, it became one of the most complex and costly spacecraft ever built. Yet the shuttle also transformed what was possible. It assembled the International Space Station piece by piece. It launched the Hubble Space Telescope, repaired it in orbit, and made science accessible to the world. Its losses, Challenger in 1986 and Columbia in 2003, served as painful reminders that spaceflight would never be routine. Every ascent, no matter how advanced the technology, demanded respect for the physics that ruled it. Meanwhile, Europe entered the race with the Ariane series, launching from the equatorial jungles of French Guiana. The European Space Agency's Ariane 5 became a symbol of precision and endurance. Its twin solid boosters and cryogenic main stage lifted communication satellites, weather probes, and interplanetary missions. In time, it would carry one of humanity's most ambitious telescopes, the James Webb, into deep space. And still, the skies grew busier. Japan, China, and India built their own launchers, each adding to the growing fleet of heavy-lift systems capable of reaching orbit. But there was a problem that all nations shared: cost. Every launch destroyed millions in hardware. Every mission required months of preparation. The dream of cheap, repeatable spaceflight remained elusive. Then, in the early 2000s, a seismic shift began, not from a government but from a small group of engineers in California. SpaceX, led by a software entrepreneur named Elon Musk, proposed a radical idea: rockets that could land and fly again. Many dismissed it as impossible, too unstable, too risky. But within a decade, the world watched as Falcon 9 boosters descended from the sky, legs extended, landing upright on barges in the ocean. It was an image no less iconic than Apollo's first step on the moon. For the first time, spaceflight was sustainable. SpaceX had done what governments could not: make orbit a commodity. Each reused stage slashed costs, transforming access to space from an elite pursuit into a viable industry. And with its triumph, others followed. Rocket Lab in New Zealand built the Electron, a carbon fiber launcher for small satellites. Blue Origin developed New Shepard and New Glenn, pushing reusability further. China announced fully recoverable rockets of its own. In less than 2 decades, the monopoly of space had shattered. But even as rockets evolved from expendable giants to agile, reusable machines, the same truth endured. Reaching orbit remained one of the hardest things humanity had ever learned to do. Every launch, no matter how routine, was still a controlled disaster that barely succeeded. The engines of fire had changed shape, but not their nature. They were still wild, barely tamed forces, our only means to escape the planet that made us. And as the rockets climbed higher, their purpose began to shift. We no longer sought just to leave Earth, we wanted to stay there, to build, to live. The next great challenge would not be about reaching orbit. It would be about what to do once we were there. Far above the clouds, in the thin silence where the blue fades into black, a silent fleet circles endlessly. They do not roar like rockets or gleam like aircraft. They drift, precisely, purposefully, keeping watch. These are the satellites, the unblinking eyes of civilization. Every day, hundreds of them trace invisible paths through low Earth orbit, their journeys guided by the subtle geometry of gravity and velocity. Some observe the Earth's magnetic field. Others map the weather, track storms, or monitor the slow breath of oceans and forests. A few drift much higher, locked over the same patch of ground, staring forever down at the same spinning globe. Together, they form an orchestra of observation, a quiet, constant conversation between Earth and sky. Among these are the Sentinel satellites, part of the European Space Agency's Copernicus program. They fly in synchronized low Earth orbits, sweeping across the poles every 100 minutes, capturing high-resolution images that reveal the shifting face of our planet. Each pass builds a living archive of the Earth's surface, Melting glaciers, spreading wildfires, encroaching cities, and the endless rhythms of climate and change. Far above them, another fleet, the GOES weather satellites, hover motionless above the equator. Locked in geostationary orbit, they rotate at exactly the same rate as Earth itself, gazing constantly at the same hemisphere. From that vantage point, they watch hurricanes form, typhoons grow, and lightning storms burst across the continents. Their data saves lives, guiding aircraft and warning coastal cities long before disaster strikes. And higher still, beyond the reach of maintenance or rescue, probes like New Horizons leave Earth's gravity entirely. Launched on flyby trajectories, they race into the outer darkness, past Jupiter's vast storms, past the frozen plains of Pluto, into the uncharted frontier of the Kuiper Belt. Unlike the sentinels that circle home, these explorers will never return. They are forever outbound, carrying humanity's curiosity to the edge of the solar system. But all of these marvels, the weather sentinels, the science probes, the communications constellations, depend on a single brutal truth: they must be launched flawlessly. Once in orbit, there are no repairs, no second chances. A single malfunction means a billion-dollar instrument becomes just another shard of metal circling the planet. To place a satellite precisely into orbit demands both brute force and elegance. The launcher must reach a velocity of nearly 8 kilometers per second, fast enough to counter Earth's gravity, but not so fast that it escapes into the void. Every kilogram of fuel, every angle of ascent, every second of burn must be calculated with unerring accuracy. The tiniest deviation can mean catastrophe. The challenge is immense, and so are the costs. Designing a satellite means building for extremes. The vacuum of space, the swing between searing sunlight and freezing darkness, the constant bombardment of radiation. Every circuit must endure years without maintenance. Every solar panel must survive micrometeorite strikes. In the void, reliability is the only insurance. And yet, despite these obstacles, satellites have multiplied. What began as a handful of Cold War experiments has become a sky filled with thousands of orbiting machines. Their signals now govern nearly every aspect of modern life. Weather forecasts, GPS navigation, global internet, crop monitoring, financial transactions, even the synchronization of electrical grids, all depend on the steady heartbeat of these silent guardians. But with their growing numbers comes a new danger: congestion. Orbit is no longer empty. Defunct satellites, fragments of old rockets, and debris from past collisions drift like shrapnel, each piece capable of destroying another in a chain reaction of destruction. A single broken satellite can unleash a cascade of fragments that turn a useful orbit into a lethal minefield. Scientists call it the Kessler syndrome, a nightmare scenario where debris generates more debris, trapping future missions under a storm of man-made meteors. To prevent that future, agencies around the world have begun designing smarter satellites, ones that can deorbit themselves, that burn up harmlessly after completing their missions. Engineers are even testing robotic servicers, spacecraft that can dock with aging satellites to refuel or nudge them to safer orbits. The Sentinels are evolving. They're no longer passive observers. They're becoming participants, reparable, adaptable, almost alive in their capacity to work together. And as they multiply, they're revealing something extraordinary. From their combined data, magnetic field readings, atmospheric maps, spectral analyses of the oceans, we are beginning to see the Earth not as separate systems, but as a single breathing organism. A living planet whose pulse can be read from the stars. These silent sentinels do not speak, yet they tell us more about our home than any explorer before them. They have shown us a fragile world, changing fast. And in their watchful gaze, they remind us that our reach into space is not just about leaving Earth, it's also about understanding it. The next chapter in this story would demand even greater machines. To build them, humanity would need to master the art of assembly, not in factories but in orbit. The age of the space station was about to begin. For 100 kilometers above the surface, where the faint whisper of the atmosphere still brushes against orbiting metal, a vast human-made structure drifts silently across the night sky. To the unaided eye, it looks like a moving star, bright and steady, crossing the heavens in just a few minutes. But through telescopes and cameras, its true form is unmistakable, a sprawling silver lattice of solar wings and pressurized modules. This is the International Space Station, the largest, most complex machine ever assembled in orbit, and the most expensive construction project in human history. It is both laboratory and home, a fragile oasis of air and warmth in the endless cold of space. The dream of such a station was born not from peace, but from rivalry. In 1984, near the end of the Cold War, U.S. President Ronald Reagan announced plans for a permanently manned space station within a decade. It would be called Space Station Freedom, a symbol of American ambition at a time when the Soviet Union was still sending cosmonauts aboard its own orbital platform, Mir. The Soviet Mir had already proven that humans could live and work in orbit for months, even years. Its modular design, assembled piece by piece using robotic docking, became a model for what a future station might be. But as Freedom stalled in political and budgetary gridlock, Mir thrived. While NASA's shuttles were grounded following the Challenger disaster in 1986, Russian cosmonauts continued building, experimenting, and surviving in the void. When the Berlin Wall fell in 1989 and the Soviet Union collapsed soon after, the geopolitical landscape changed forever. What had begun as a race between enemies suddenly became an opportunity for cooperation. In the ashes of competition, the seeds of collaboration took root. NASA and the newly formed Russian space agency, Roscosmos, began an unprecedented partnership. The Americans would bring funding, logistics, and the shuttle. The Russians would bring hard-earned experience in long-duration flight. Together, they would merge their separate dreams into a single shared vision. A new international outpost, built in orbit, assembled by hand, and occupied by crews from every corner of the planet. The first piece was launched in November 1998, a cylindrical module called Zarya, Russian for sunrise. 2 weeks later, NASA's Space Shuttle Endeavour carried Unity, the American-built connecting node, and linked it with Zarya in orbit. For the first time, Russian and American hardware became one spacecraft. The new station had no crew, no laboratories, not even electricity yet. But it was alive. Over the next decade, the ISS would grow from this small beginning into a city in space. Using robotic arms and daring spacewalks, astronauts and cosmonauts assembled solar arrays, trusses, and research modules in a process more complex than any construction on Earth. Each component had to align with millimeter precision, and every connection had to hold under the harshest conditions known to engineering: vacuum, radiation, and extremes of temperature. For the first permanent crew, launched aboard Soyuz TM-31 in 2000, the ISS was little more than a skeleton. Commander William Shepard of the U.S. and cosmonauts Yuri Gudzenko and Sergei Krikalev arrived to find a half-built home. They unpacked supplies, installed systems, and slowly brought the station to life. From that day onward, humans have never left low Earth orbit empty. Someone has always been there, circling the planet every 90 minutes. As new modules arrived, Europe's Columbus Laboratory, Japan's Kibo, Canada's robotic arms, the ISS became a truly global project. 15 nations contributed to its design, construction, and operation. Each launch was a small miracle, a symbol of what humanity could achieve when it worked together rather than apart. Yet even this triumph came at a cost. The loss of the Columbia shuttle in 2003 halted construction for nearly 4 years. During that time, all access to the station depended on Russian Soyuz spacecraft and Progress cargo ships. What had begun as America's dream of independence in space became, ironically, a lesson in dependence and cooperation. Still, the work continued. By the time the final space shuttle mission, Atlantis, departed in 2011, the ISS had grown to a volume larger than a 5-room house, powered by 8 massive solar wings. Inside, astronauts floated between laboratories and sleeping quarters, conducting experiments on human physiology, fluid dynamics, material science, and biology, research impossible on Earth. From the ground, Mission controllers monitored oxygen levels, water recycling, and power output, keeping the station alive with constant vigilance. Each orbit was a balancing act between gravity and speed, between survival and discovery. But beyond its scientific mission, the ISS represented something deeper. It was a monument to resilience, to the idea that after decades of rivalry, humanity could build something greater together than apart. Above national borders, beyond politics, it stood as a shared frontier, a reminder that Earth itself was one fragile home. And yet, as the years passed, questions began to arise. How long could such an aging outpost endure? Its modules were built for 15 years, yet they had already surpassed that. The cost of maintenance was rising, and new players, private companies, emerging nations were preparing to build their own stations. The ISS had marked the end of an era, the age of state-owned dominance in space. A new generation was waiting in the wings, smaller, faster, cheaper, and far more daring. The next leap would no longer come from governments, but from visionaries with rockets of their own. When the Space Shuttle Atlantis touched down for the final time in July 2011, the world entered a strange silence. For the first time in half a century, the United States had no vehicle capable of sending humans into orbit. NASA's fleet was grounded, its astronauts suddenly passengers aboard Russian Soyuz spacecraft. The great age of government-run exploration seemed to be fading. Yet in that silence, a new kind of energy was building quietly, stubbornly, in warehouses and workshops far from any space agency. The dream of flight beyond Earth had escaped the grasp of nations and found new life in the hands of private innovators. The space frontier was opening not through politics, but through entrepreneurship. Among those pioneers was a man many in the aerospace industry initially dismissed, Elon Musk. In 2002, he founded SpaceX with an ambition so audacious it bordered on absurd, to build rockets that were both affordable and reusable. Musk's logic was brutally simple. Every other transportation system in history became practical only when it could be reused. Throwing away rockets after a single flight, he argued, was like scrapping an airplane after one trip across the Atlantic. The traditional aerospace giants, Boeing, Lockheed Martin, Northrop Grumman, scoffed. Rockets were far too complex to survive re-entry and landing. They were controlled explosions, not airliners. But SpaceX, unburdened by decades of bureaucracy, started small and learned fast. The Falcon 1, their first orbital rocket, failed 3 times before finally reaching orbit in 2008. That single success changed everything. NASA took notice. With the shuttle program retired, the agency turned to private partners to deliver cargo to the International Space Station. SpaceX won one of the first contracts. Their new rocket, the Falcon 9, carried the Dragon spacecraft, capable of not only delivering supplies, but returning safely to Earth. In 2012, when Dragon docked with the ISS, it became the first commercial spacecraft in history to do so. But Musk's ambitions didn't stop there. He wanted to land his rockets vertically, precisely, on Earth after every launch. The idea sounded like science fiction. Even NASA's most advanced engineers considered it impractical. Yet in December 2015, a Falcon 9 booster descended through the night sky, flames roaring in reverse, and touched down gently on its landing pad at Cape Canaveral. Humanity had just watched a rocket do the impossible. From that moment, the space industry transformed overnight. Each reused booster saved tens of millions of dollars. Launch frequency skyrocketed. Costs plummeted. Suddenly, orbit was no longer the exclusive realm of superpowers. It was accessible to startups, universities, even small nations. Others followed. In New Zealand, Rocket Lab emerged with its carbon fiber electron rocket, designed to deliver tiny satellites to low Earth orbit at record low cost. Its 3D printed engines and electric pumps broke nearly every convention of rocket design. In Texas, Jeff Bezos's Blue Origin developed the New Shepard and New Glenn rockets, focusing on reusability and suborbital tourism. Even Europe, long reliant on the Ariane family, began planning cheaper, modular systems to compete. The days of monolithic, government-built rockets were fading. A new ecosystem was forming, fast, flexible, and ruthlessly innovative. Launches became routine events, streamed live online to millions of viewers. A generation that had grown up watching space shuttle launches on grainy television now watched boosters land on drone ships in the middle of the ocean. But this revolution wasn't just about lowering costs. It was about redefining what space could mean for humanity. With smaller, cheaper rockets, thousands of new satellites could be deployed, forming vast constellations like SpaceX's Starlink, designed to blanket the planet in internet coverage. For the first time, connectivity itself would come from the stars. Critics warned of overcrowding, of orbital debris and interference. But the momentum was unstoppable. Private industry had turned space into a marketplace, launch services, satellite data, communications, even asteroid mining. The once mythical domain of astronauts and superpowers had become a playground for entrepreneurs and engineers. And yet, amid this new dawn of opportunity, a deeper question began to emerge. Was humanity democratizing space, or simply commercializing it? Could private corporations, driven by profit, steward the heavens responsibly? For all the excitement of reusable rockets and mega-constellations, the same risks remained. Launch failures still happened. Explosions still claimed payloads. And space itself, as vast as it seemed, was finite. A fragile shell of orbit easily scarred by recklessness. Still, the revolution continued, driven by competition, innovation, and a lingering dream that began with Sputnik. Humanity had learned not just to visit space, but to live with it, to use it, and perhaps one day to thrive in it. As one generation of engineers turned their gaze to Mars, another began to look closer to home, at the machines already out there, circling quietly in the dark. Machines that needed care, maintenance, and sometimes repair. The next chapter of the story would not be about rockets launching from Earth, but about the delicate art of keeping what we had already built alive. Every 90 minutes, the International Space Station completes a full orbit around the Earth, 16 sunrises and 16 sunsets every single day. From its windows, astronauts can watch the world spin below them in breathtaking silence. The glowing ribbons of auroras curling around the poles, lightning storms flickering across continents, the golden arcs of cities sparkling at night. Yet inside that beauty lies the constant hum of machinery, the subtle hiss of air circulation, the faint vibration of pumps and fans. Life in orbit is not tranquil. It's sustained by unceasing vigilance. For the astronauts aboard, the ISS is both home and laboratory, an island of humanity afloat in the void. Every breath, every sip of water, every heartbeat depends on technology functioning flawlessly. Systems must recycle everything: air, moisture, even the carbon dioxide exhaled by the crew. Nothing is wasted. The station is a closed ecosystem, a fragile bubble of life surrounded by vacuum. Days in orbit follow strict routines. Astronauts wake to the rhythm of mission control, often greeted by music from Earth. Their schedule is divided into segments measured to the minute: exercise, maintenance, research, meals, communication, rest. 2 hours of physical training per day are mandatory. Without gravity, muscles weaken and bones lose calcium rapidly. Even sleep becomes an adaptation. Astronauts float in zippered sleeping bags anchored to the walls, in darkness punctuated by the glow of instrument panels. Outside, work continues on the surface of the station itself. Spacewalks, known as EVAs or extravehicular activities, remain among the most dangerous tasks in all of exploration. Protected only by thin layers of polymer and metallized fabric, astronauts step into an environment that is both silent and lethal. Temperatures swing from plus 120 degrees Celsius in sunlight to minus 150 degrees Celsius in shadow. The Earth below is beautiful, but also indifferent. Every tool must be tethered, every movement rehearsed. A single drifting wrench could puncture a module or become high-speed debris in orbit. Repairs that might take minutes on Earth can require hours of careful maneuvering. And yet, despite the risks, these walks are essential. The ISS endures constant exposure to radiation, micrometeoroids, and thermal stress. Panels degrade, joints seize, sensors fail. Human hands, protected by layers of Kevlar and insulation, remain the best tools for keeping the station alive. Inside, the research never stops. Scientists use the station's microgravity environment to study how materials behave without weight, how flames burn, how fluids flow, how human cells grow. They test drugs that may counter bone loss or radiation damage, study the effects of long-duration flight on the heart and brain, and even grow protein crystals too delicate for Earth's gravity. Each experiment adds a thread to the tapestry of knowledge that will one day allow humans to survive journeys far beyond orbit. But there's another, quieter kind of research happening aboard the ISS, one about ourselves. Astronauts are living test subjects for the future of interplanetary travel. Every heartbeat, every blood sample, every psychological survey feeds into an understanding of how isolation, confinement, and cosmic radiation shape the human body and mind. In this floating lab, camaraderie becomes a lifeline. Crews are international. Russians, Americans, Europeans, Japanese, Canadians, and more. They share meals, fix leaks, and laugh together in a place where every mistake could be fatal. The simple rituals of humanity, sharing tea, taking photos of home, playing guitar, carry an enormous emotional weight. When conflicts arise, they are solved not through politics, but through patience and professionalism. In orbit, cooperation isn't optional, it's survival. Over the years, the ISS has weathered crises both mechanical and human. Air leaks have appeared suddenly, forcing rapid repairs. Computers have failed mid-mission. Spacecraft have docked at awkward angles. Yet through it all, the station has endured, a testament to the strength of teamwork across borders and languages. Still, time is catching up with it. Some of its modules have been in orbit for over 2 decades, long past their design life. Metal fatigues, seals weaken, and the cost of maintaining the structure grows with each year. Engineers on Earth debate the future. Should the ISS be replaced by smaller, private stations? Should its legacy be extended, or should it be allowed to burn up in the atmosphere, a fiery farewell to an age of cooperation? Whatever its fate, the ISS remains one of humanity's greatest experiments, not only in science but in trust. It has proven that people can live and work in space for years, that nations can share resources and goals, and that humanity can thrive even in places where life was never meant to exist. And as it orbits endlessly above us, another generation is already preparing to take its lessons further. Plans for lunar stations, Mars habitats, and commercial outposts are on the horizon. The experience gained aboard the ISS will guide them all. Because before we can leave Earth for good, we must learn one thing above all: how to live together safely, wisely, and humanly among the stars. When the Space Shuttle Discovery carried the Hubble Space Telescope into orbit in April 1990, few imagined how profoundly it would reshape our understanding of the cosmos. Suspended 547 kilometers above the Earth, free from the distortion of the atmosphere, Hubble became humanity's clearest window into the universe. Yet its beginning was anything but flawless. Just weeks after its launch, scientists made a shocking discovery. Hubble's primary mirror had been ground to the wrong shape by a margin thinner than a human hair. The result: a faint but devastating blur in every image. The world's most expensive telescope, meant to reveal the distant stars, could barely focus. Newspapers called it a $1.5 billion blunder. But failure, as space exploration has always proven, can be the seed of brilliance. In December 1993, NASA launched Endeavour on one of the most ambitious missions ever attempted, a full orbital repair. Using robotic arms and human hands, astronauts installed corrective optics, transforming Hubble from a flawed mirror into a scientific marvel. When the first sharp images returned, crisp, luminous, breathtaking, they silenced every critic. Stars no longer smeared into fog. Galaxies sharpened into spirals. Humanity was seeing the universe as never before. Over the decades that followed, Hubble's lens became our collective eye. It witnessed the birth and death of stars, mapped the vast scaffolding of galactic clusters, and measured the expansion of the universe with unprecedented precision. It captured the pillars of creation in the Eagle Nebula, columns of gas and dust sculpted by radiation, photographed with such clarity that they became icons of cosmic beauty. It found galaxies so ancient that their light had been traveling since the dawn of time itself. But Hubble's impact wasn't only scientific, it was emotional. For the first time, humanity saw itself as part of a universe vast and alive. Its images appeared in classrooms, on screensavers, in museums, and on the walls of children's bedrooms. It made the abstract tangible. Space was no longer an empty void. It was art, history, and destiny combined. Keeping Hubble alive required human devotion. Across 5 servicing missions, astronauts replaced its gyroscopes, instruments, and solar panels. They upgraded its cameras, computers, and sensors, turning it from a 1990s relic into a constantly evolving observatory. Each mission was a ballet of precision, performed hundreds of kilometers above Earth, where one mistake could mean disaster. But each time, Hubble came back stronger. By the early 2000s, Hubble had become more than a telescope, it was a legacy. And yet, even legacies must evolve. In the deserts of California and the clean rooms of Maryland, engineers began constructing its successor, the James Webb Space Telescope. If Hubble was humanity's eye, Webb would be its deep vision, able to see farther into time, beyond even the first galaxies, into the cosmic dawn. Unlike Hubble, Webb would not orbit Earth. It would travel 1.5 million kilometers away to the L2 Lagrange point, where the gravity of the Sun and Earth balance perfectly. There, shielded by a sunshade the size of a tennis court, it would operate in infrared, detecting the faint heat signatures of stars and planets invisible to the human eye. The road to launch was long and fraught with delays. Budgets exploded, mirrors cracked, wiring failed. The telescope became a symbol of human impatience and of human persistence. When it finally launched on December 25, 2021, aboard an Ariane 5 rocket, billions watched with held breath. Every stage, from deployment to calibration, had to succeed. One wrong move could doom decades of work. And yet, like Hubble before it, Webb triumphed. In July 2022, NASA released its first images. Fields of galaxies stretching across time, their light bent by gravity into shimmering arcs. Nebulae glowed in colors no human had ever seen. The deep universe opened like a door. Together, Hubble and Webb tell a single story, a story of vision. They remind us that exploration isn't only about going farther, but about seeing deeper. One looks at the visible cosmos, the other at its ancient echoes. Hubble taught us how to dream. Webb teaches us how to remember. These telescopes also changed how we think about ourselves. When astronauts gaze at Earth from orbit, they see the fragility of home. When astronomers gaze outward through Hubble or Webb, they see its insignificance and its rarity. The Earth is one spark in an ocean of darkness, yet it's the only one that glows with life. From the ISS to Hubble to Webb, our vantage points keep expanding. Each new eye we open in space allows us to reflect more deeply on who we are and what we might become. And as we look outward, the question begins to turn inward. How will we survive when we finally leave the cradle of Earth? That question leads us to one of the most vital and overlooked technologies of all, the armor that keeps humans alive where no life should exist. The story of the spacesuit. Before rockets, before orbit, before the dream of walking on another world, there was a question so simple it almost sounded absurd. How does a human survive where there is no air? A spacesuit, at first glance, looks like a costume, white fabric, mirrored visor, patches of national flags. But beneath its surface lies one of the most complex life support systems ever built. A miniature spacecraft worn on the body. It must regulate temperature, provide oxygen, remove carbon dioxide, manage waste, and protect against radiation and micrometeoroids, all while allowing the wearer to move, see, and work. It is, in every sense, a personal habitat in the void. The journey to create that shell of survival began long before spaceflight. In the 1930s, aviators pushing the limits of altitude discovered that beyond 12 kilometers, the air grew too thin to breathe and too cold to endure. Engineers began developing pressure suits for high-altitude pilots, early ancestors of the modern spacesuit. They were crude, bulky garments of rubberized fabric and metal joints, designed to keep the body from expanding in the near vacuum above the stratosphere. When the first astronauts were chosen in the late 1950s, they inherited these designs. The American Mercury suit was little more than a modified high-altitude flight suit, shiny aluminum-coated nylon, flexible but sealed tight. It was meant not for walking, but for survival inside a cramped capsule. Astronauts wore it as insurance, a final layer of defense in case their spacecraft lost pressure. As missions grew more ambitious, so did the suits. The Gemini program of the mid-1960s tested the first spacewalks, and with them came a new challenge: mobility. Outside the capsule, astronauts had to twist, reach, and maneuver while maintaining internal pressure. Engineers soon realized that every bend of a joint required enormous effort. In vacuum, even simple movement becomes a battle against one's own suit. Then came the Apollo era, the moment when humanity would step onto another world. The A7L spacesuit, developed by ILC Dover and worn by Neil Armstrong and Buzz Aldrin, was a masterpiece of function and endurance. Layers of nylon, Teflon, mylar, and Dacron formed a pressurized cocoon. Its visor reflected lethal sunlight. Its boots bore the first human prints on the moon. It allowed freedom of motion while holding 3.7 psi of internal pressure, enough to keep the human body alive in the vacuum of space. But those suits were not comfortable. Astronauts described the lunar surface as like working in a balloon. Every step was resisted by pressure. Every grip required force. Inside, sweat pooled, cooling systems strained, and oxygen tanks dwindled. Yet they worked. For a few brief hours on the moon, humanity lived without a planet beneath its feet. The post-Apollo years brought new designs for new environments. On Skylab and later the shuttle, suits evolved into modular systems. The Extravehicular Mobility Unit (EMU) became the gold standard, a mix of hard metal torso, flexible arms and legs, and a self-contained backpack known as the primary life support system. Every EVA from the shuttle to the ISS has relied on its reliability. Astronauts train for months underwater, simulating zero gravity, learning to move with care and precision in what one NASA veteran called the world's most expensive piece of clothing. Each suit tells a story of adaptation. The Soviet Orlan, rugged and efficient, could be donned in minutes and operated by a single cosmonaut. The American EMU emphasized precision, modularity, and long-duration maintenance. Both became icons of human engineering, different philosophies united by the same goal: keeping fragile bodies alive where nothing else can. Today, the frontier of suit design is shifting once again. As NASA prepares for Artemis missions to the moon, engineers are creating the XEMU, a new generation of suits capable of supporting longer, more flexible lunar excursions. It allows astronauts to kneel, climb, and work in lunar dust without exhausting themselves. Meanwhile, private companies like SpaceX and Axiom Space are developing their own suits, sleeker, lighter, tailored for future commercial missions and even space tourism. But beyond design and technology, there's something symbolic about these garments. To wear a spacesuit is to wear the sum of human ingenuity. Every seam, every joint, every fiber is a declaration. We do not belong here, but we refuse to be denied. It is also a humbling reminder of fragility. One puncture, one faulty valve, one loose cable, and the difference between life and death is measured in seconds. Astronauts know this, that awareness shapes their every move, every breath, every glance at the Earth below. From the first pressure suit to the latest exosuit, the evolution of the spacesuit mirrors our progress as a species. Each generation of engineers has asked the same question: how can we make survival possible in a place where it shouldn't be? And answered it with fabric, air, and faith. And now, as humanity stands on the threshold of returning to the moon and journeying to Mars, these suits will once again become our second skin. For when we take that next step onto alien soil, it won't just be machines exploring. It will be humans, shielded in their fragile shells, carrying all of Earth within them. Because every exploration, no matter how far it reaches, begins with the same truth. Before we can conquer the stars, we must first conquer our own limits. Every generation of explorers believes it is the first to glimpse the unknown. Yet every rocket launch, every orbit, every photograph from the stars carries the echoes of those who came before. Space exploration is not just a timeline of missions and machines. It is a living inheritance, passed from one era of dreamers to the next. The legacy of exploration began long before Hubble's shimmering images or the ISS's glowing trails in the night sky. It started with the mathematicians, philosophers, and astronomers who dared to imagine that Earth was not the center of everything. When Copernicus placed the sun at the center of the cosmos, he set in motion a revolution that would one day propel rockets skyward. Galileo's telescope revealed the moons of Jupiter. Kepler's equations mapped the paths of planets. Newton's laws gave us the mechanics of flight long before we could build it. By the 20th century, imagination had turned to invention. In Russia, Konstantin Tsiolkovsky, the quiet schoolteacher often called the father of astronautics, proposed that humanity could one day travel to space using liquid-fueled rockets. In Germany, Hermann Oberth and Wernher von Braun turned theory into engineering, designing engines that would eventually lift men to the moon. Across the Atlantic, Robert Goddard tested his rockets in the fields of Massachusetts, ridiculed in his lifetime but vindicated by history. When the Sputnik beeped across the skies in 1957, it wasn't merely a signal from a metal sphere. It was the culmination of centuries of thought. Humanity had finally reached the threshold that dreamers and scientists had described for generations. And yet, what defines our legacy in space is not just our triumphs, but our persistence in the face of failure. The Apollo 1 fire that claimed 3 astronauts in 1967. The Challenger explosion in 1986. The loss of Columbia in 2003. Each tragedy carved deep scars into the history of exploration, but none ended it. Instead, every failure forced us to rebuild, rethink, and continue. The courage of those lost became the foundation of every mission that followed. Legacy also lives in what we've left behind. On the moon's surface, 6 flags stand stiff in the vacuum, their colors bleached by sunlight. Scattered around them are footprints that will remain for millions of years, untouched by wind or rain. Nearby lie tools, lunar rovers, and a small metal plaque that reads, "We came in peace for all mankind." But perhaps our greatest legacy isn't physical, it's cultural. The first images of Earth from space changed how we see ourselves. The famous blue marble photograph, taken by Apollo 17, showed a fragile, luminous world floating in darkness. For the first time, nations, borders, and conflicts vanished into a single shimmering sphere. That image became an emblem of unity, sparking the modern environmental movement and redefining our sense of belonging. Space exploration also reshaped technology on Earth in ways few predicted. The need for lightweight materials, advanced communications, and precise computing led to innovations that now power smartphones, GPS systems, and medical imaging. From satellite weather forecasting to solar energy, the tools we use daily are the children of our cosmic ambitions. But beyond technology and science, the legacy of spaceflight is human. The astronauts who orbit above us are ambassadors of cooperation. When a Russian cosmonaut and an American engineer share a meal aboard the ISS, they embody a truth that transcends politics. Above the Earth, humanity is one species. Still, this unity remains fragile. Even as nations collaborate in orbit, competition brews on the ground. China's Tiangong station, India's lunar landers, and the Artemis program's return to the moon all signal a new, multipolar age of exploration. Yet perhaps this rivalry is not a curse but a catalyst. The same competitive spirit that once ignited the first space race now fuels the global pursuit of discovery. As we look back on the path from Sputnik to Starlink, from Vostok to Voyager, we see a single unbroken thread: the refusal to accept limits. Space is not our natural home, and yet we build, we launch, we endure. The legacy of exploration is not the technology itself, it is the mindset behind it. Because when we gaze at the night sky today, filled with satellites and stations, telescopes and debris, we are not just looking at the products of our civilization. We are looking at the reflection of a species that will not stop asking questions, even when the answers lie light years away. And now, that legacy faces its greatest test. For the next steps in exploration will push us farther than ever before, beyond Earth's orbit, beyond the moon, into the deep and hostile reaches of interplanetary space. The question is no longer whether we can go. It's whether we can survive once we get there. For centuries, Mars has haunted human imagination. Its reddish glow, visible even to the naked eye, has inspired stories of gods, wars, canals, and civilizations long lost. But in the age of satellites and science, Mars became something more than myth. It became a mirror. A world so close to our own, and yet utterly alien. A reminder of what Earth could become, and perhaps what it once was. The dream of reaching Mars was born before the first rocket ever flew. Visionaries like Wernher von Braun imagined armadas of spacecraft ferrying settlers across the void, building cities under glass domes. Science fiction filled in the gaps of science itself, making the impossible feel inevitable. But reality, as always, proved more complex. Reaching Mars is not just about distance, it's about survival. Even at its closest, the planet lies 55 million kilometers away. A round-trip journey could take nearly 3 years. Every gram of food, every drop of water, every molecule of oxygen must be carried, recycled, or created en route. Communication delays stretch up to 20 minutes one way, turning every problem into an isolated puzzle. And then there's radiation, an invisible storm of cosmic rays and solar particles that can tear through human DNA. Yet despite these challenges, the path to Mars has already begun. Slowly, piece by piece, through the probes and rovers that have paved the way. In 1965, NASA's Mariner 4 sent back the first close-up images. A cratered, desolate world that shattered dreams of life. Later missions, Viking 1 and Viking 2, searched for microbial traces, finding chemical mysteries that scientists still debate today. The rovers that followed, Spirit, Opportunity, Curiosity, and Perseverance, became our mechanical explorers, rolling patiently across alien soil. They found dried riverbeds, ancient deltas, and minerals that could only have formed in water. Mars, it turned out, was once alive with motion, a place where lakes shimmered and rain may have fallen. Each mission has brought us closer, both technologically and psychologically. The landers have taught us how to survive the descent through a thin, unpredictable atmosphere. The orbiters have mapped resources and terrain for future landing sites. The Perseverance rover carries something unprecedented. A small helicopter named Ingenuity, the first powered flight ever achieved on another planet. For the first time in history, we have not only landed on Mars but taken to its skies. But the next step, the human step, is the hardest. NASA's Artemis program aims first to return astronauts to the Moon, using it as a proving ground for Mars. Lunar missions will test habitats, radiation shielding, and resource extraction from local materials. Meanwhile, private companies like SpaceX are racing to make interplanetary travel feasible. Its Starship, a towering stainless steel rocket capable of carrying 100 people, represents the most ambitious vehicle ever built. Fully reusable, refueled in orbit, it could, in theory, bridge the gulf between worlds. For Musk and his engineers, the goal is clear: to make humanity multiplanetary. Mars, they argue, is not a destination, it's a backup plan. A safeguard against extinction, a new frontier for civilization. Critics call it naive or reckless, pointing out that we have yet to solve our crises on Earth. But for others, it is the purest expression of human hope, the refusal to stay confined to one fragile world. Governments are listening. NASA, the European Space Agency, and even China have announced long-term plans for crewed Mars missions. Each follows a similar pattern: develop sustainable propulsion, build orbital depots, test long-duration habitats, and eventually launch small crews for a mission that will redefine exploration forever. Yet the road ahead is steep. Mars is a place that punishes mistakes. Its air is unbreathable, its soil toxic, its storms immense. Temperatures plunge to -100 degrees Celsius at night. Dust coats everything, clogging joints and solar panels. Even the simplest human gesture, removing a glove, stepping outside unprotected, would mean instant death. Still, we move forward. Because to stand still is to deny the essence of who we are. The mission to Mars will not be easy, nor quick, nor cheap. It may take decades, generations, or longer. Some of the first travelers may never return. But their footsteps, like Armstrong's, will echo beyond their lives. They will mark the beginning of something new, humanity's transformation from a planetary species into an interplanetary one. And perhaps, centuries from now, when children on a red horizon look up at a small blue star shining faintly in the Martian dusk, they will remember that once, long ago, their ancestors looked at that same star and dreamed of reaching them. Because the greatest legacy of exploration is not where we go, it's that we keep going. From orbit, Earth looks eternal. Its oceans glowing blue, its continents painted in ochre and green, wrapped in thin curls of white cloud. But every astronaut who has gazed down from that vantage point says the same thing: the planet looks fragile. The atmosphere, our only shield, is as thin as a line of smoke against the blackness of space. One tear in that veil, and the miracle of life we take for granted could vanish. Space exploration has always been driven by ambition, by the desire to reach farther, see deeper, and push beyond our limits. Yet, paradoxically, it has also forced us to look inward. The farther we go, the more we understand how rare and precious our world truly is. Every mission to the moon, every image from Hubble, every probe that ventures into the dark carries an unspoken reminder: there is no other home like Earth. This realization was never more profound than in December 1968, when Apollo 8 circled the moon. As the spacecraft rose from the lunar horizon, astronaut William Anders captured a photograph that would change history: Earthrise. Against the barren gray of the moon, the Earth floated like a fragile ornament, half in sunlight, half in shadow. That single image transformed humanity's perception of itself. For the first time, we saw our world as one, a tiny, living sphere adrift in an endless void. It was no coincidence that, just a few years later, the environmental movement ignited around the globe. Satellites soon revealed deforestation, desertification, melting glaciers, and changing oceans in stark clarity. The same technology that carried us into space began teaching us how to protect the world we were leaving behind. Whether satellites warned of hurricanes, Earth observation systems tracked the pulse of forests and reefs. Data from orbit reshaped agriculture, energy, and disaster response. Space exploration, in a way, became a guardian of Earth. It gave us distance, and with it, perspective. But that perspective also carries a warning. The resources that power our rockets, the materials that build our stations, and the debris that clutters our orbit, all remind us that progress has a price. Each satellite launch adds fragments to the thin shell of space around our planet. Some burn up harmlessly, others remain. Metal shards circling at bullet speeds. A collision between two defunct satellites can unleash thousands of fragments, each capable of destroying another. Scientists call this the Kessler syndrome, a runaway chain reaction that could one day make low Earth orbit too dangerous to use. In a strange twist of fate, our reach for the stars could threaten the very bridge that connects us to them. That is why today's engineers speak not only of exploration, but of sustainability, both on Earth and beyond. Space agencies now design satellites with built-in deorbit systems, ensuring they burn up after use. International partnerships track debris, sharing data to avoid collisions. Meanwhile, environmentalists look to space as both warning and guide, using orbital data to monitor carbon emissions, pollution, and the shrinking cryosphere. The balance is delicate. Humanity must learn to expand without consuming, to explore without destroying. Even as nations prepare to build lunar bases and send crews to Mars, many scientists argue that the most urgent frontier is still our own planet. Climate models built from spaceborne data warn of rising seas, burning forests, and shifting weather patterns that could redefine the very notion of home. In this light, our quest for the stars becomes not an escape, but a rehearsal. If we can learn to sustain life on barren worlds, perhaps we can relearn how to preserve it on our own. It is a paradox that defines the age of space. We look outward to understand inward. The more we study alien worlds like Venus and Mars, planets once wet, now dry and dead, the more we see the future that could await Earth if we forget its fragility. This awareness has begun to shape a new philosophy of exploration, one not of conquest but of coexistence. The International Space Station, once a symbol of competition turned to cooperation, has become a floating emblem of unity. Astronauts often describe a phenomenon called the overview effect, the overwhelming realization, upon seeing Earth from space, that all divisions, political, cultural, religious, are illusions. From orbit, there are no borders. There is only one world, shared by everyone. As we stand at the edge of a new era, returning to the Moon, reaching for Mars, sending telescopes beyond the limits of sight, the lesson is clear. The farther we go, the more we are called to protect the place from which we came. Because space, for all its wonder, is indifferent. It does not care whether we survive or vanish. The stars will continue to burn, the galaxies to spin, long after we are gone. It is up to us to decide whether our legacy will be one of harmony or hubris. In the end, the greatest challenge of space exploration may not be how to live among the stars, but how to remain worthy of the one planet that already sustains us. And as we prepare for the next leap, into deeper space, into unknown worlds, we must ask the question that has lingered since the dawn of the first rocket. Are we ready to carry Earth's fragile balance into the darkness? For as long as we have looked up at the stars, one question has burned brighter than all the rest. Are we alone? It is a question older than civilization, older than science, perhaps even older than language itself. Every generation of explorers, from Galileo to the engineers of Voyager, has carried it silently within their hearts. For most of human history, the heavens were a mystery we could only imagine. But once we learned to send machines beyond Earth's atmosphere, the question of life beyond became not only philosophical but experimental. We could finally look, listen, and measure, and what we found has both deepened and complicated the mystery. The first clues came not from distant stars, but from the planets next door. When Mariner 9 mapped Mars in 1971, it revealed dry river valleys and ancient floodplains, evidence that water, the elixir of life, once flowed freely there. Decades later, NASA's rovers confirmed the discovery. The red planet had once been a world of lakes and streams. If life could have taken root anywhere beyond Earth, Mars seemed the most likely cradle. But Mars was only the beginning. As telescopes sharpened and probes ventured farther, new worlds began to reveal their secrets. Beneath the icy crust of Jupiter's moon Europa, the Galileo spacecraft detected a global ocean of salt water larger than all of Earth's combined. Saturn's moon Enceladus, once thought inert, was found to be venting towering plumes of water vapor into space. Within those plumes, NASA's Cassini probe detected complex organic molecules, the chemical fingerprints of life's building blocks. Suddenly, the universe no longer felt empty. It felt unfinished, alive with possibility. And then, in the mid-1990s, came a discovery that changed everything. Astronomers found the first planet orbiting a star beyond our sun, an exoplanet. Within a decade, dozens more followed. Within 2 decades, thousands. The Kepler Space Telescope alone identified over 2,600 confirmed worlds, and the James Webb Telescope now peers deeper, searching for atmospheres that might contain oxygen, methane, or carbon dioxide, the telltale signatures of biology. These discoveries reshaped our place in the cosmos. What once seemed extraordinary, the idea of other worlds, has become inevitable. The Milky Way may contain more planets than stars. And among those billions, countless lie in the so-called habitable zone, where liquid water could exist. If even a fraction of them host life, the galaxy could be teeming with it. And yet, we have heard nothing. This silence is what physicists call the Great Filter, or more poetically, the Great Silence. If life arises easily, why haven't we detected it? Where are the signals, the structures, the evidence of civilizations beyond our own? Perhaps, some say, intelligent life destroys itself before it learns to reach out. Perhaps communication across interstellar distances is impossible. Or perhaps, most hauntingly of all, they are out there and simply choosing not to answer. For decades, scientists have listened. The SETI, Search for Extraterrestrial Intelligence, program scans the skies for artificial radio patterns that nature could not produce. The Breakthrough Listen project, funded by private donors, now surveys millions of stars across billions of frequencies, searching for whispers amid the static. And occasionally, just occasionally, something stirs. Unexplained bursts, narrowband tones, momentary patterns. Each time, hope flares. Each time, it fades into noise. But silence does not mean solitude. Even if intelligent civilizations remain undiscovered, microbial life, simple, ancient, enduring, might still fill the universe. The discovery of even one alien microbe, one fossilized bacterium, one unmistakable biosignature on another world would redefine biology, philosophy, and religion forever. It would prove that life is not a miracle of Earth, but a property of the cosmos itself. And perhaps, in some way, that answer has already begun to emerge. The organic chemistry of comets, the amino acids found in meteorites, the detection of phosphine gas in Venus's atmosphere, all suggest that life's ingredients are scattered freely among the stars. The seeds are everywhere. Perhaps they only need time. Yet the search is not only outward, it is inward. Every signal we send, every probe we launch is also a reflection of ourselves. When Voyager 1 and Voyager 2 departed the solar system, they each carried a golden record, engraved with the sounds and images of Earth. Greetings in 55 languages, the sound of rain, the laughter of a child, the pulse of a heartbeat, and a simple message of peace. Somewhere, drifting through interstellar darkness, those records are still traveling. Our first attempt to say, we are here, and maybe someday, somewhere, someone or something will find them. Until then, the silence remains. But perhaps silence is not absence. Perhaps it is invitation. Because the universe is vast beyond comprehension, and we are only beginning to listen. The story of space has always been the story of thresholds. Each generation stepping beyond the last, each success revealing new questions waiting in the dark. But now, at the dawn of the 21st century's third decade, a new kind of space age is emerging, one defined not by competition, but by convergence. Science, industry, and imagination are merging in ways even the architects of Apollo could never have foreseen. The universe has become a living laboratory. Private companies launch missions once reserved for nations. Artificial intelligence pilots probes, designs trajectories, and analyzes data faster than any human team could. Three-dimensional printing builds rocket parts on demand, even in orbit. Robotic explorers prepare landing zones before astronauts ever arrive. The boundaries between science fiction and engineering are blurring, quietly, steadily, irreversibly. Nowhere is this transformation clearer than on the moon. After decades of silence following Apollo, humanity is returning, not as visitors but as builders. NASA's Artemis program leads the way, aiming to land the first woman and the next man on the lunar surface. But this time, they won't be planting a single flag. They'll be laying foundations. Using lunar regolith for construction, extracting water ice from the poles for fuel and oxygen, the moon will become both a laboratory and a launch pad. Other nations are joining. China's Chang'e missions have already landed rovers on both the near and far sides of the moon, with plans for a joint base by the 2030s. India's Chandrayaan 3 touched down successfully at the South Pole, proving that even emerging nations can reach the lunar frontier. Japan, the European Union, and private consortia are developing their own landers and orbiters, preparing for a new lunar economy built on cooperation and competition. This isn't just exploration, it's infrastructure. Communication relays, fuel depots, solar farms, each component inching humanity toward a sustainable presence beyond Earth. The moon is no longer the destination. It's the first stepping stone to everywhere else. Beyond it, Mars still waits, red, cold, and tantalizingly close. But while the journey there remains perilous, the technologies that will make it possible are already being tested. Closed-loop life support systems aboard the ISS, autonomous navigation aboard rovers, radiation shielding printed from local materials, and long-duration habitats designed for months of isolation. The blueprint of interplanetary civilization is being drawn piece by piece, orbit by orbit. Even farther ahead, dreams stretch beyond the solar system itself. Proposals like breakthrough Starship envision fleets of gram-sized probes propelled by laser sails, reaching the nearest star, Proxima Centauri, within a human lifetime. Nuclear thermal and fusion propulsion systems, once the realm of theory, are re-entering serious development. What began as a race to orbit may one day become a journey between stars. But amid this expansion, a quieter revolution unfolds: the democratization of space. The once exclusive realm of superpowers now includes universities, startups, and even high school projects. CubeSats, tiny modular satellites, study everything from climate change to cosmic radiation. Amateur astronomers detect exoplanets. A new generation of explorers is learning that space is not somewhere out there. It's part of daily life. And with that realization comes responsibility. As access broadens, so must ethics. Who owns the moon's resources? Who protects fragile extraterrestrial environments from contamination? What happens when nations or corporations lay claim to places that belong to no one and everyone at once? The frontier is expanding faster than the laws that govern it. The challenge ahead is not only technological, it is moral. Still, for all its complexity, this new era carries a familiar heartbeat: curiosity. The same impulse that guided the first stargazers still drives the engineers programming autonomous rovers. The same wonder that lifted Sputnik and Apollo now fuels students launching CubeSats from school rooftops. The tools have changed, but the desire remains timeless. Perhaps this is the truest measure of humanity's progress, not how far we've traveled, but how deeply we've continued to ask why. Why explore? Why risk? Why reach into the dark when there is so much left to understand at home? The answers, as always, are found not in the machines, but in the minds that build them. Each rocket, each satellite, each telescope is an extension of that ancient curiosity, the need to see, to know, to belong to something larger than ourselves. And so, the next horizon isn't just physical. It's philosophical. It's the moment we realize that space is not a place we visit. It's a dimension of who we are. Beyond the atmosphere, beyond the moon, beyond the farthest signal ever sent, the story continues. Humanity stands again on the edge of the unknown, not as conquerors, but as participants in a universe that is vast, silent, and waiting. The next chapter is already being written, in circuits, in starlight, in courage. And its first words are the same ones that have guided us since the beginning. Let's go farther. Every frontier hides a shadow. For all its triumphs and discoveries, the story of space has always carried a quiet warning, a reminder that every step forward brings new dangers, both physical and moral. The same engines that lift telescopes and satellites into orbit can also deliver weapons. The same technologies that promise abundance can spread inequality. The same silence that fills the void between stars can also reflect our own. As humanity pushes deeper into space, we stand at a crossroads between progress and peril. Never before have we possessed so much power, or so little understanding of how to wield it responsibly. Already, the militarization of orbit is no longer science fiction. Nations have tested anti-satellite weapons, destroying their own satellites in displays of power that scatter debris across space. Intelligence platforms, once meant for observation, now track every launch, every transmission. The space around Earth is not only a laboratory, it's becoming a battlefield of data, surveillance, and deterrence. Yet these same orbital systems also hold the key to cooperation and peace. Satellites synchronize global communications, monitor treaty compliance, and detect natural disasters faster than any ground-based system ever could. They are both sword and shield, depending on how we use them. The question is not whether space will shape the future, but who will shape it and for what purpose. Meanwhile, technological progress is accelerating faster than ethics can follow. Artificial intelligence now designs spacecraft, predicts weather systems, and interprets deep space signals. Quantum encryption promises unbreakable communication, but also the potential for absolute secrecy. Biotechnologies tested in orbit hint at the possibility of adapting the human body for life beyond Earth. What was once the domain of philosophers, what does it mean to be human, is rapidly becoming a question for engineers. And beneath it all lies the fragility of our own planet, glowing softly below. The view from orbit reveals both wonder and warning. The thin line of the atmosphere, the retreating ice, the expanding deserts, each orbiting astronaut becomes an unwilling witness to the cost of human ambition. Space exploration, for all its grandeur, reflects a civilization still learning how to balance creation and consequence. But perhaps that is why we explore, not because we are perfect, but because we seek to become better. Each discovery forces us to confront ourselves. When we look at the dead seas of Mars or the burning clouds of Venus, we see echoes of our own future if we fail to listen. When we gaze at the distant blue of Earth, we see a chance to choose differently. In that sense, the edge of tomorrow is not a place. It's a moment, a test. Humanity's expansion into space is the ultimate mirror of our values. Will we carry with us the divisions, greed, and carelessness that scarred our home world? Or will we finally learn, among the stars, what it means to be caretakers of life rather than conquerors of it? There is reason for hope. Around the world, new generations of scientists, artists, and dreamers are reimagining what exploration means. They speak not of empires, but of stewardship. Not of conquest, but of continuity. Private space ventures now pledge to offset carbon footprints, recycle rocket stages, and share open data for planetary protection. Astronomers advocate for dark and quiet skies, defending the natural night against constellations of artificial light. Engineers develop satellites that will one day clean debris instead of adding to it. In classrooms and laboratories, children build their first model rockets and stare at images from the James Webb Telescope. Images that make them realize how small and how connected we all are. It is from this awareness that the promise of the next century will grow. Because in the end, the true frontier is not out there, it is within us. Space does not change who we are. It reveals us. Every reflection in a visor, every photograph from orbit, every signal from the dark shows the same fragile, persistent truth. Humanity is one species, bound to one destiny. And standing at the edge of tomorrow, we must decide whether that destiny will rise with the stars or vanish beneath them. The next part of this story is already approaching, a conclusion not of endings, but of echoes. The universe is waiting for our answer. From the moment the first rocket pierced the sky, humanity began to rewrite its own story. In a few short decades, we've gone from lighting fires in caves to lighting engines that burn brighter than the sun. We've looked back at our planet from the edge of infinity and realized how small, and yet how extraordinary, we truly are. The long view of space is humbling. Everything we've ever known, every empire, every discovery, every heartbeat, has unfolded on a single fragile sphere of rock orbiting an ordinary star. In the grand architecture of the cosmos, Earth is a microscopic thread in a tapestry that stretches beyond imagination. And yet, it is our thread. It is the only one we can touch. For all our progress, the universe remains vast, cold, and silent. The light from distant galaxies takes billions of years to reach us, carrying messages from an age before Earth existed. Stars are born, flare, and die in the span of human forgetfulness. Even our sun, giver of life, will one day fade into embers. Against that immensity, human time is barely a whisper. But that whisper matters. Because within it lies awareness, the rarest phenomenon we know. The cosmos is full of matter and motion, but only here on this pale world has it learned to look back upon itself and ask, why? That question, so small, so human, may be our greatest achievement. Every satellite orbiting above us, every rover exploring the dust of Mars, every telescope peering into the abyss, all of them are extensions of that ancient curiosity. They are our eyes and our hope, scattered across the heavens. They remind us that exploration is not about escaping Earth, but understanding it. It is not about leaving home, it is about seeing home clearly for the first time. And perhaps, one day, when we finally reach other worlds and build new homes under foreign suns, we'll carry with us more than machines and mathematics. We'll carry music and laughter. We'll carry the memory of oceans, the scent of rain, the stories of who we were. The stars will not erase our origins. They will illuminate them, because no matter how far we travel, we will always be children of Earth. Its soil in our bones, its light in our blood. The future of exploration will not be a single great leap, but countless small ones. Private stations circling the moon, autonomous ships mapping the outer planets, networks of telescopes decoding the first light of creation. Some of these steps we'll witness. Others will unfold long after we're gone. That continuity across generations, across centuries, is what defines a civilization that endures. And maybe that is the true destiny of our species. Not to conquer the stars, but to become a part of them. When the Voyagers left the solar system, they carried not just instruments, but messages, golden records engraved with the voices, sounds, and music of Earth. Somewhere, billions of kilometers away, those records drift through the dark. Long after our cities crumble and our oceans shift, they will still carry our greeting to the universe. A testament that, once, there was life here that looked up and dared to reach out. Perhaps no one will ever find them. But that isn't the point. The act of sending them, the decision to speak into the cosmic silence, is itself a declaration of hope. Because to explore is to believe that there is something worth finding. And in that belief lies everything that defines us. So as we gaze upward, from our small blue world spinning in the dark, we are reminded that the journey is not over. It has barely begun. The horizon will always recede, and we will always follow. Not out of arrogance, not out of conquest, but because the universe is vast, and life is rare, and curiosity is the most human thing we have ever known. And somewhere, beyond the clouds, beyond the silence, beyond the reach of time itself, the stars are waiting.